Polymer chemistry has revolutionised science over the last century, with the most important developments notably in plastics. Plastics are used in our daily lives for the interests of safety, such as food packaging, convenience with the typical plastic bag, and ease, due to their durability, lightweight and chemically inert structure, from long, non-polar hydrocarbon and monomer chains. The most widely used and produced polymers include polyethylene in its high density and low density version, which are produced from the cracking of crude oil to give different monomers, but with the same unreactive hydrocarbon backbone. However, this is a non-renewable resource and there is pressure on finding similar, low-cost yet durable plastics. But most importantly, what do we do with the plastic once it has served its primary purpose or we can no longer reuse it? The attractive features of plastics, which allow them to serve their main purpose, ultimately leads to issues concerning their disposal. The addition polymers contain strong, non-polar long chains which take hundreds of thousands of years to naturally biodegrade through the attack of enzymes or microorganisms, or by further reaction. This is due to their unreactive nature of the chain, with its length and strong dipole-dipole forces between each CH, and therefore, unfortunately, they tend to accumulate in landfill sites, as litter in the streets, or worse, in the oceans, endangering the lives of many animals along the way. The development of biodegradable plastics with properties that make them as effective as their non-degradable counterparts have become very important. Biodegradation is based on the concept that a natural or synthetic polymer can be broken down naturally and takes place through the action of enzymes and or chemical deterioration associated with living organisms. This occurs by fragmentation of the polymers into lower molecular mass species by means of either adiabatic reactions such as oxidation, photodegradation, or hydrolysis. Furthermore, biotic reactions are becoming more sustainable with degradations by microorganisms. Polylactic acid is synthesized from starch extracted from crops like corn, cassava, and sugar canes, whilst polyhydroxyalcohols, also known as PHA, are synthesized by having bacteria feed on vegetable oils or sugars from food crop. This provides a hopeful alternative, as sourcing natural polymers may lead to the biodegradability answer. Using the hydrolysis breakdown of polylactic acid, which is sourced from corn, starch or sugar, can lead to petroleum-based polymer substitutes. These constrict under heat and have similar properties of that of their synthetic counterparts, making them attractive. It is made from a new renewable food source that is relatively low cost to produce in terms of energy required. Yet there is an ethical argument over whether a food source should be used for consumer goods over food. Polylactic acid can biodegrade in around 60 days to 12 months to form CO2 and H2O via a hydrolysis reaction. Yet conditions have to be just right for this to occur, so this doesn't solve the landfill issue, as specialist techniques are required. Natural degradation can also limit its uses in some industries where a non-polar polymer may be more suitable. Commercial biodegradation uses very high temperatures, so it is still environmentally questionable due to the use of fossil fuels to generate this. If commercial composting isn't available either, polylactic acid plastics can end up winding up following conventional plastics into the landfill or into plastic recycling programs. So what is hydrolysis? Hydrolysis of the polymer chain is used to gain an ester functional group. Hydrolysis reactions result in the breakdown of polymers into monomers by using a water molecule and an enzyme catalyst, breaking the covalent bonds that hold monomers together in the polymer chain by an endothermic reaction. This reaction is suitable for condensation polymers such as polyesters, polyanhydrides, polyamides, polyethers and polycarbonates, all of which have varied uses, with polycarbonate becoming one of the most widely used engineering thermoplastics because of its high impact strength and heat resistance. These polymers can be produced by alkenes undergoing a condensation reaction followed by polymerization, such as the reaction of alkenes to form carboxylic acids and alcohols, which can then form ester linkages through the loss of water in a condensation reaction. They can then be further broken down by a hydrolysis reaction with dilute acid or alkaline catalysts or enzymes in the appropriate chemical environment, such as correct temperature, pH, and the need for a water nucleophile. Though this polymer can be biodegraded, its chains are more reactive than the addition polymer and can therefore be attacked by unwanted nucleophiles at any stage, and this limits its usage in some industries. However, their biodegradability can also be limited, as in the wrong environment, such as the ocean, the breakdown cannot be achieved, not solving the problem of plastic pollution in the ocean. Furthermore, some methods still rely on the production of alkenes from crude oil for mass production. Another hopeful method includes the uses of microorganisms and bacteria. Polyhydroalkalates are synthesized from having bacteria feed on vegetable oils or sugars from food crop, but various bioplastics are made from algae using heating and cooling methods, as well as mixing with calcium carbonate. New biodegradable materials include the use of microorganisms which can be used to produce polymers, such as PHB, also known as polyhydroxybutyrate. This is produced by organisms under restricted growth conditions to produce a brittle polymer with a melting point close to its degrading temperature. This makes the polymer difficult to work with, and hence copolymers are favoured. Difficult synthesis and purification steps leading to low yields are avoided by using microorganisms, but the resulting polymer's usage and effectiveness in industry makes it an unattractive substitute. Starch and cellulose are also used as natural polymers with similar chains and are most commonly used in biological processes. Their ability to be biodegraded and long, strong chains open the possibility of a future alternative for addition polymers, with starch being added to the chains of some polymers to help aid biodegradation. But synthesis for a long-term substitute for other polymers have not yet been widespread. As with all polymers and scientific techniques, there is a list of pros and cons which limit their usages. For biodegradable plastics, they do not release dangerous side products upon decomposition, such as methane and CO2, which reduces the threat to the environment, such as plastic in oceans. Though this cannot be said for all substitute, it is favourable over the typical addition polymer. It also leads to cleaner urban and rural environments. Petroleum-based plastics do not decompose in an eco-friendly manner, which can leave waste products scattered throughout the communities, which is a benefit of these biodegradable substitutes. In some instances, biodegradable polymers can just be as effective as their petroleum-based counterparts in terms of their properties. Mostly, they are also made from renewable resources, which makes them more favourable in the long run. However, there is downsides to these polymers, such as farmland use and water use to actually produce the raw material. There's also the ethical issues, such as using a food source to generate energy or a consumer good when it could be going towards helping solve poverty. There's also the disputed use of pesticides and other chemicals on the sugar and cane. It's not as low cost as addition polymer production. Synthesis can require more energy as well. But overall, in an ideal scenario, all bioplastics would end up in an industrial compost, but realistically this is not the case in the short term. Some bioplastics will inevitably end up in landfills, where, deprived of oxygen, they may release methane. This is a greenhouse gas 23 times more potent than carbon dioxide, so it is imperative that we educate the public on the need to dispose of these plastics correctly.